Okay, welcome Ralph and Jordan, Caesar and Jesus and Victor and Jacob. This is our week 6, actually. We're just about halfway through the class. And today is kind of a regular day. We don't have a big test coming up. We didn't, not giving back a test or anything like that. So it's just good old fashioned linear algebra. And let me share my screen, talk about what we're doing today. Okay, so hopefully you can see what I'm looking at. Today is a day about linear transformations. And what we're going to be looking at is, as always, I'll start out with Q&A. And then after that, we'll say, well, a linear transformation is a function. So given that it's a function, we could talk about its range. And then, so pretty much we're going to do all the function stuff today. After talking about the range, we'll talk about what does it mean for a linear transformation to be a one-to-one linear transformation. And the nice thing is same definition of function, if you remember it. And then after that, we'll talk about what it means to be onto. So we'll look at that. And then we'll say, well, we kind of know about functions, one-to-one and onto. Now let's make it special. And linear transformations are matrices. Okay, at least the ones we've learned so far. And so now the question is, if it's a one-to-one linear transformation, or if it's an onto linear transformation, what can you say about its matrix, and vice versa? So we'll talk about that. And then we'll look at compositions of linear transformations. Okay, and it turns out, not a big surprise, same as composition of functions, and all the theorems still work. And then we'll get into isomorphisms. Very important, also not that hard. Today's not one of the harder days. A lot of theorems, but nothing too tough. I think you'll agree when you see it. And then after talking about isomorphisms, we'll say, well, what about the inverse of a linear transformation? Because a linear transformation is a function, and functions sometimes have an inverse. And what is an inverse of a linear transformation? And we'll take a look at that, and how does that relate to its matrix? And the good news is, I think you'd all guess if I asked you to, tell me, how does the inverse of a linear transformation relate to the transformations matrix? So then we'll get into inverse and compositions, and then we'll get into bases. So we've talked about what a basis is, and we'll say, well, if you have a linear transformation, what does it do to a basis? And we'll find out it can do nice things if it is an isomorphism. And then TFAE. So since we will have some new stuff with linear transformations, and we'll be able to relate it to matrix, and then we'll be able to go TFE. So that is the plan of today. So hopefully it'll go well. Again, I don't think it's one of the harder ones, but maybe you'll think so. I don't know. But let me ask you, are there any questions? That could be about homework. It could be about anything else coming up. Open this one up. Usually there's a few. Give you a minute to think.
Was it supposed to be so easy, the homework from Friday? I felt like it was pretty simple.
Well, I shouldn't say this, but all the homework's easy for me.
Well,
so it's hard for me to tell exactly, is it easy or is it hard? It's easy if you understand it. And that's kind of how this whole class is. And it's hard or brutal if you don't. So if it was easy, that probably meant you understood it. Or it meant that you didn't at all, and you did it and had no idea that you were doing everything wrong. But
yeah, that's what I'm kind of worried about.
Hopefully not. And I'll know that when I grade it. But if you have any questions on any of them, I can help. No questions? This might be a first, actually, for our class. We might finish early if there's no questions. but I can always make more stuff to do. No questions? Okay, if there's really no questions, maybe I'll mention something I wasn't going to spend time mentioning, but I might as well now. And that is, we'll meet again on Wednesday. And then we have a whole week off. Do you realize that? Or a week minus, huh?
Do we meet on Friday too?
We don't meet Friday, and we don't meet a week from today.
Huh.
Yeah, so we have a whole week off. Actually, it's a week minus 1 hour and 45 minutes because we meet until 2:45 on Wednesday, and then we start the following Wednesday at 1 o'clock. So it's a week minus 1 hour 45 minutes is off. Okay,
Is
you'll
that
still huh?
for the whole school or just this class?
Well, just this class, because if you have a Tuesday Thursday class, you still meet on Thursday and Tuesday, right? But the whole school, the whole college is closed on, I mean, we're always closed, but the classes aren't in session at all, even online, this Friday and a week from Monday, because it's President's Day weekend. So it's not me getting creative, by the way. So just note, so that's the way it is. I don't even have any plans yet. It's supposed to snow, I think. We'll see how it goes.
So you aren't meeting this Friday, and next Wednesday we meet at 1:45?
No, 1 o'clock.
Okay.
Yeah, we meet regular time, but we don't meet at all on Friday, and we don't meet at all a week from today because it's the President's Day weekend, right? And that's standard at our college. We always do that, and pretty much all the colleges, I think. Okay, any other questions? Okay, if there's no questions, maybe we'll get into the big definitions. But I'm going to have you guys see if you can figure it out first. Who remembers what it means to say the range of a function?
What are all
A
the
set of all of the outputs.
Okay, good. The set of all the outputs, right? Okay, or you can say the set of all values of y such that there exists an x such that f of x equals y. Kind of a little more formal. Okay, well, linear transformations, and I hope you get it, are functions. Do you all know that? Given an input, there's a unique output. That's what a function is. It has a domain, it has a range. The domain is Rn and the range is Rm. So a linear transformation is a function. And since it is a function, we can actually define its range the same way we've always done. So here's our definition of range. And again, it shouldn't be surprising at all. And that is the range of a linear transformation is the range as it is defined as a function. Set of all y. So it's that t of x equals y. This is the one time I'm using x and y like the book does instead of v for vector, because I want you to kind of make it feel like a function. And it feels like you should plug in x and get a y, because that's what functions are. Any questions about the range? Any questions? Okay. It turns out that there are ways of finding the range. Just like for functions, functions actually can be harder. I don't know if you remember, but finding the range of a function can be really brutal sometimes. Sometimes easy, but sometimes brutal. Linear transformations are never that bad as long as we understand it. So let's do it. Let's do an example. So let P go from R2 to R2. Let's go R3. Be such that T of the vector 1, 2 is equal to 0, 1, 1, and t of zero comma negative one is equal to 1 comma 0 comma 1. What is the range of t? Okay, so we have a question here. And first thing I want to ask you, is this question actually well defined? So have I given you enough information to know exactly what t is? What do you
Yeah.
think?
Yeah, we can get a matrix for the transformation here.
Yeah, and how do you know you can?
Because we have two of the outputs of the transformation.
It's not the outputs that matter, it's the inputs. What about the inputs though?
They are not multiples of each other.
And because they're not multiples, what does that imply?
They are
That they're
products.
linearly independent.
Yeah, linearly independent.
I'm looking for a better word.
They are the basis.
They're a
for-
basis. Yeah, they're a basis for R2. And if you say what a linear transformation does to a basis, then we know what it does to anything. Okay, whereas if I didn't give you where a basis, 1, 2, comma 1, 2, and 0, negative 1, then this wouldn't be defined. I couldn't even ask the question. Is that clear? So that's kind of a review from last time. All right, so now that we know it's a basis, now we can talk about what is the range. And the idea is to find the range, what we can do is we can find the matrix first. How do you find the matrix of a linear transformation?
You just turn the output vectors of the transformation into columns for your matrix, right?
That's great for convenient bases. That's as the book calls it. But we have an inconvenient definition. Do you remember what that means? Can you remember?
It'll
It
be
won't work for that
specific
sort of thing.
inputs.
Yeah, in particular, it's not the standard basis. See, you turn the 1, 0, 1, 1 and 1, 0, 1 into columns if you're given what t does to the standard basis, but this isn't the standard basis. So we have to do an extra piece. Do you remember what that is? I'm gonna open that up. There was an extra little bit. Nobody's jumping in. I'm gonna get it ready while you're thinking about it, and hopefully you can tell me. So remember, we take the matrix of columns of the inputs, or the input basis, which is 1, 2, and 0, negative 1. What do we do with that matrix? Do you remember?
We need to find the inverse.
Yep, we need to find the inverse. And then what we do is we multiply by what?
The matrix of the output.
Yeah, we multiply by the matrix of the output. Any questions on that? So, and in particular, we do the inverse first and then we do the output. So we multiply kind of backwards in a way. So let's do that. Where am I? There. So we multiply by 0, 1, 1. And 1, 0, 1. Any questions at all on that? And let me write that. I'll just call that AT, which is the matrix of the linear transformation T. Any questions on doing that? Okay, and notice this works because if you start out with the standard vector, like 1, 0, then it'll give you, if you start out with 1, 0, then it'll give you the 1, 2, and then you can apply the 0, 1, 1 to it. Do you remember doing this?
Yeah.
Okay. Now, what's the inverse of this matrix? First thing, is it invertible?
Yes. The determinant's non-zero.
Exactly. The determinant is -1. Nice, easy determinant. So now we can actually calculate this. And this inverse now will be, first thing, the determinant is -1. And then you remember you switch. So remember how to find the determinant of a 2 by 2. Do you remember the technique?
Yeah, you swap A and D and then put negatives on B and C and then multiply it by the determinant, 1 over the determinant.
Okay. And the interesting thing is and then the 1 over the determinant is -1. So the interesting thing is if I swap A and D and multiply by -1, guess what? It's 1 and -1 again. Kind of cool. If I take 0 and 2, make them negative and multiply by -1, guess what? I get 0 and 2. So I kind of made a really easy one. Got lucky. So that inverse is itself. Isn't that cool? One of the rare matrices where the inverse is itself, but it can happen.
What does it mean when the inverse of a matrix is itself? Is there any special property? Or is it just something that sometimes happens?
It's something that sometimes happens. There's lots of special properties. So there are special properties of it, and it can happen. So it means A squared is the identity, right? Because A times A is I. So it has lots of special properties, but nothing we've done yet. But what it means is that if you apply the matrix, so imagine a matrix in a 2 by 2. Then last time I showed you what it looks like when it acts on the plane. Do you remember that?
Yeah.
So what this says is if you act on the plane with the matrix and then act on it again with the matrix, you're back to where you started. Is that clear?
Yeah, that makes sense.
Yeah. So doing the matrix twice does nothing to the plane. And that's kind of geometrically what it means. Okay. Whereas doing it once actually does do something to the plane, but doing it twice does nothing. Okay. So now we go ahead. And now we can write down oops. Doesn't want me to get rid of that thing, so I won't. So now I can write down what I get when I'm done. I'm going to just put this one in because it's easier to copy and paste and plug in. And what do you get for the first entry?
2.
2. And then let's read by rows. The next entry?
-1.
And then the next?
1.
Yep, 1. And the next one? 0.
Yeah.
And then the next one?
1 or 3.
And then finally, -1. Any questions on that? Any questions? Now it turns out, and we'll talk about this a little later, it turns out that when you have a linear transformation, and if we know what it does to a basis, that one thing that's all you need, and that's what we've got. And it turns out that a basis is also, so one of the bases is 2, 1, 3, -1, 0, -1, but it's also 0, 1, 1, 1, 0, 1, and that's just because. We'll prove that a little later. Any questions on the idea of the range?
What was the range exactly? The basis of T?
Yeah, so the range is 2, 1, 3 is the first vector, and -1, 0, -1.
Okay.
So it's just the matrix for the transformation that's the range, or?
Well, it's the columns of the matrix.
Oh, okay, all right.
Yeah, yeah. So it's the columns. I didn't write it out because it's a pain to type it out, but I can read the column and say that's the first one, and the second column is the second one. Okay. Now, important definitions that come right from kind of intermediate algebra. And again, a big thing of what we're doing today is we're looking at just functions that you learned about when you were in, I don't know, whatever grade you were in when you had intermediate algebra first. You know, that might have been 11th grade or 10th grade or who knows. And we're thinking about all the things we know about functions and realizing linear transformations are functions. So we can take the idea of the function, we can say, okay, we have a linear transformation. So we have the definition already. And then you could say, what does it mean? Like, what's the, not just the definition, but what does it tell us and what does it give us? Does that make sense? So here's a definition. All these definitions are definitions you've already had. You had it in whatever grade you were in when you had intermediate algebra the first time. So that is, if T is a linear transformation and it's a one-to-one linear transformation, then T of V equals T of W implies that V equals W. Isn't that one-to-one? Do you remember that from functions? Or is that like, never heard of it before?
This is just a fancy way of saying that, like, if two outputs are equal, then they have to have the same input, right?
Yeah. So this isn't a linear algebra word. This is an intermediate algebra word. You know, you've had it for years. You may not remember it because it's been so long. Okay, but it's important. And another word for one-to-one function is that if T is one-to-one, we call T an injection. Okay, so that's just a word. There's nothing to explain there. It's just a word called injection. Any questions on the idea of one-to-one? Okay, when was one-to-one important? Last quarter. Don't you hate when I say that? When was a one-to-one linear transformation important? Last quarter.
Jacobians?
Yeah, what about them?
I'm not entirely sure.
Can you remember? Turns out the Jacobian is not one-to-one, okay? If the linear transformation from the Jacobian is not one-to-one, then you can't do it. You're actually not allowed to, it just doesn't work. So if you have a transformation that's not one-to-one, then you can't use it to find volume, for example, in a triple integral. I don't know if Bruce talked about that, did he? Maybe you don't remember because it's been so long, not sure. Okay, but it did come up in a big way, is that you have to have it to be one-to-one, or you can't even do it.
Because it wouldn't even make sense to have it be equal, right?
Yeah, because what it does is it changes the dimension if it's not one-to-one.
Yeah.
So if it's not one-to-one, then you could start out with some three-dimensional solid, do the transformation, and now you have a two-dimensional shape, because that's what happens when it's not one-to-one. And that's bad. Good luck finding the volume of a two-dimensional shape. Do you see? and the Jacobian, the 1 over the Jacobian is going to be undefined, you just have all kinds of problems. Okay, so 1-to-1 turns out to be essential for applications. It's a big deal. There's not too much more to say about it other than this is what it is. Okay, I'll talk about how to find it, but we need a little theorem before we get there. But any questions on this definition? Okay, now comes the next definition, kind of is, I wouldn't say the opposite, but it's, I don't know, in conjunction with 1-to-1. It's the other biggie. And who remembers what that is? It's always a word after 1-to-1. Always the definition in algebra. Not our class necessarily, but.
Would it be ratio?
It wasn't ratio. All right, maybe I'll tell you. Onto. Okay. And then maybe I'll do a theorem after. I think I'll put that after because let's get into onto, because that's really what's supposed to be after 1-to-1. So T is onto, let's make that red. If the range of T is all of Rn, okay, or of all of whatever you want the range to be. Any questions on that idea? So that means that if you give me any vector in Rm, okay, then I can find a vector in Rn such that T of my vector is your vector. Any questions on that? Okay, and the word we often use for that is we'll say T is a surjection. So remember, 1-to-1 transformations are injections, and onto transformations are surjections. Any questions on this definition? Any questions? Okay, if there's no question, let's get to a theorem that's a nice, important, useful theorem. And it says the following: T is 1-to-1 if and only if for T of V equals 0 implies that V equals 0. Okay, so the nice thing about this theorem is if you want to show something's 1-to-1, you don't have to show that any two of them go to the same place, because that's a lot harder than just saying, hey, if you get to 0, you must have started at 0. Any questions on that idea? All right, so we want to prove this. Okay, so first thing, if T is 1-to-1, I could say maybe let T be 1-to-1 because it's a proof. Okay, and let T of V equals 0. What are we trying to show?
That V is equal to 0.
Yeah, we want to show V is equal to 0. Okay, how do we prove that V is equal to 0?
Multiply by T inverse to both sides.
He might go from R2 to R8. There's no inverse.
Because we saw the definition of linear transformations.
Okay, when you say the definition, what definition are you using?
When K times B equals 0, that means that, or we are multiplying by 0 or B equals 0.
Yeah, and that's not the definition, it's a theorem. So let's use a theorem. So theorem from Friday. That's right, Friday's theorem. I didn't give it a name, so I'm just gonna call it Friday's theorem, which is kind of what you're talking about, right? we do know that what's T of 0? Always.
0 vector.
Yeah. This is kind of what you're talking about, right? We know T of 0 is 0, period. Okay. So the idea here is that if V is not 0, then what can we do? What can we apply T to?
T of 0v.
Okay. T of 0v. Yeah, but that's not going to help.
Okay.
Yeah, the 0v is what got us the T of 0, 0. Okay, so the idea here, if T is not 0, we want to show that T of V is not 0, right? Okay, is that clear? But why must that be true? Well, what haven't I used yet?
It's 1-to-1.
Yeah. So I didn't even do T of, but I can say then this breaks 1-to-1 because both V and 0 go to 0. Therefore, is that clear? Because 1-to-1 says if you have two things that go to the same place, then the two things must have been the same thing. Well, guess what? I got two things that both go to 0. So therefore, V equals 0. So V can't not be 0. Any questions on that? Anyone lost? So what this tells us is if we want to show something's 1-to-1, we don't have to show that T of V equals T of W implies V equals W. All we have to do is show that if you end up with 0, you get 0. Now, within matrix language, what's the language for the stuff that goes to 0? What are the words? It's 2 words.
Standard basis.
No, the standard basis doesn't all go to 0. That's for sure. I mean, not with a 1-to-1 transformation, definitely.
Row reducible.
No, keep trying. You're getting there.
Just a space or a subspace?
There's actually 2 words. There's a certain type of space or subspace. There's 2 words that mean the same thing. Remember?
Span. And
Good try. You're throwing all the linear algebra words I can hear.
yeah.
Null
Get there,
space.
maybe. Huh?
Null space.
Yeah, the null space. Okay. So another way of saying, in fact, I'm going to put it in the theorem. So the null space of T, okay, maybe AT. So the matrix A with respect to linear transformation T is trivial. That's what that means, right? What's another word for null space? Remember I told you there are 2 different things you can use. Do you remember the other word? Huh?
Kernel.
Kernel, yeah. So another way of saying the same thing is the kernel of the matrix A is the 0 vector, and that's it. Any questions on this? Okay, very important theorem, very useful. We're going to be using it a lot. Okay. All right, here comes the next one. Is that if T is 1-to-1, if and only if its matrix A has rank n. T is onto, oops, I think I typed it wrong. T is onto if and only if the matrix A has rank m. There we go. Why is that true?
Because they need to be a basis, so they should be linearly independent, the input.
Yeah, I think I have the M's and N's backwards, sorry. They need to be a basis. It's not about bases. It's about a theorem we've already had. Do you remember the theorem that says that how do you find the nullity? How do you find the nullity of a matrix? I know I did have it right, and M.
Isn't it the rank of A plus the... No, that's not it.
The nullity is n minus the rank.
Yeah. So it's equal to N minus the rank of A. So guess what? T is 1 to 1 means the nullity is 0. Is that clear? Because if T is 1 to 1, then 0 is the only value in the null space. So that means the nullity is 0. So that means rank of A is N. That's the proof. That's it. That's the whole proof of that one. Any questions on that? Who's lost? All right, if I want the nullity to be 0, I better let rank of A be N from our equation from that theorem we had a while back. Okay. T is onto if and only if the rank of A equals M. Why must that be true?
T is onto if the range of T is equal to Rm.
Mm-hmm. And do you remember we had a theorem? Huh?
So therefore it must be, the rank of it must be equal to N.
Right, right. Because if you remember that the rank of A, was the dimension of the range. Do you remember that? And if it's onto, then the dimension of the range must be M or it doesn't work. Is that clear? So the rank of A is the dimension of the range. We had that theorem a while back. There's a lot of theorems in this class. And if it's onto, then the dimension of the range is M, sorry. And that's it. That's the whole proof. So the nice thing is we basically already had these theorems, just not with this language before. Any questions at all on these two theorems? Any questions? Okay. No questions at all about it? Okay. So I can do examples. Examples aren't that interesting though. So the idea is if we have a T, and T can be written as a matrix. So let's say I'll give you a matrix. Let's do it. Okay, just a note. Here's T. Can you all see it?
Yeah.
All right. Now I'm going to let you use your imagination. I'm purposely not putting numbers in. All right. No matter what I put in, can t be 1 to 1? Can t be on 2?
No. No.
One. They can't be either, you're saying?
All right. It can't be on 2
Okay, you're saying it can't be on 2. And how come?
because it's impossible for n to be the same as rank A.
Not be on 2.
All right.
Because we know that the rank of A is definitely not bigger, is less than or equal to. If I do this symbol, let's see if it lets me. Yep. Is less than or equal to what? What's the biggest the rank could be?
2.
2. Okay, so we know that the rank of A is less than or equal to 2, right? Well, what does that tell us? Well, notice that M is equal to 3. So that means T is not on 2. Any questions on that? Notice I didn't even have to put in numbers. Just by looking at this thing, you know it cannot be on 2. Is that clear? Now I'll put in numbers. How about 1, 3, 1? 2, 6, 2. Is T 1 to 1?
No.
No.
And you say no, why not?
Because they're multiples. The vectors as columns are multiples of each other.
Yeah, in particular, what I can write, and we're used to doing this, I try to make it really easy so we don't have to use symbol app. REF of A is equal to what? I try to make it easy.
1, 2, 0, 0.
Yeah, so it's the first row is 1, 2, and the last rows are both zeros. I'm not sure if you can do that in your head, but it's not that bad. So what is the rank of A? What's the rank of A in this case?
1.
Yeah, the rank of A is 1. And 1 is certainly less than, is or not equal to is a better word. Let me go to symbol not equal to. It's not equal to 2 because we have 2 columns. It's not equal to 2. There's the 2. Therefore, T is not 1 to 1. Any questions on that? What do you think the hardest part about this stuff is going to be?
When the matrix is big.
No, that's not going to be the hardest part. I bet you won't guess. Should I tell you? Okay, hardest part is to keep all the vocabulary straight because we've had a lot of language in this class. And all these words I'm throwing at you, you just have to have down. That's the hardest part. Once you have all the vocabulary straight and the basic theorems, none of this is hard. I mean, what I did, was that hard? You know, not at all. And you even get Symbolab if you didn't want to REF it in your head, but I tried to make one really easy, so you wouldn't want to use Symbolab. Any questions on that? So the hardest part is to get the words down like one-to-one and onto and rank and nullity and all these different words that we've had in our class, and get them all down and how they relate to each other. That's the hardest part. Once you have all that, nothing's hard. Have you noticed that in this class?
Yeah, if you get it, you get it.
It's not like calculus. Calculus could be rough, even if you get it. I mean, there could be some kind of, you know, integration by parts with also having to do some kind of, I don't know, partial fractions at the same time. And it's messy, even if you get it. Do you remember that stuff?
Yeah.
This isn't like that. This is just has a lot of language, a lot of theory, but the math is so easy. Any questions on this theorem? Before I move to the next one. Today's kind of theorem day. So next theorem, before we get into the next definition. Okay, so if S and T are 1-to-1, then S of T is also 1-to-1. Any questions on what the statement is?
So this is now looking at composition.
Yeah. It's a composition. So if we have S of T is 1-to-1, then S of T is 1-to-1. And it turns out the interesting thing about this one, this is not a linear algebra theorem. It turns out that this is true even if it's not a linear transformation, if it's just a function. But we should probably prove it. And the idea is, because I just told you it's true anyway, you don't need to use matrices. Okay. And you can use matrices, but actually that's harder. Instead, what can we do?
Think of two 1-to-1 functions and compose them.
We can't do it by example. That's never a proof. Right? So we have to use a definition. Okay, so let S and T be 1-to-1. I'll write linear transformations, but functions will work too. All right, well, what's the definition? So let's say, so then we got to say, well, if S, and I'll use a parenthesis way of doing it, T of V is equal to S of T of W, what's my goal? Given that we're trying to show it's 1-to-1.
We need to show that V and W are equal.
Yeah, we need to show V equals W. Okay, that's our goal. So always keep in your mind your goal. If you don't know your goal, it's really hard to get there. Do you agree? Okay, so we know what our goal is. Our goal is V equals W. What we're allowed to use is that S is 1-to-1 and the T is 1-to-1. Which one do I use first?
I'm thinking T is 1-to-1.
One more guess.
Then S is 1-to-1.
Yeah. So let me just rewrite this just to make it so that you understand what's going on. So rewritten. So let's say A equal T of V and B equals T of W. Okay, so I'm just renaming it. Are you okay with that? Then S of A equals S of B. Do you all agree all I did was substitute in just my new way of writing T of V and T of W?
Yeah.
Okay, but now S is 1-to-1, and we know S of A equals S of B. So since S is 1-to-1, what can I say?
A and B are equal.
Yep, A equals B. Okay, now let's undo the definition. What was A?
T of V.
Therefore, T of V, and what was B?
T of W.
Right, so T of V equals T of W. But T is 1 to 1. So since T is 1 to 1 and T of V equals T of W, what can I now say?
V equals W.
Any questions at all on this proof? Do you all agree it was really easy to watch?
It's definitely way easier to watch.
And if I gave it to you on a test, how many of you would get it right?
Probably not me.
If I gave it to you without just showing you now. So proofs are like that. It's like for this class at least, they're not hard if you know what you're doing. Okay, if you really have, if you're reading it, but to come up with it, that's the hard part. I do want to mention something, and this is something I mentioned when we started, but I want to re-mention it. If you look at what I did here, nowhere did I use linear transformation. Right? If I used f and g instead of s and t and just said f and g were functions, do you agree this proof still works?
Yeah.
Yeah. So if f and g are one-to-one functions, it still works. So this is a proof, but this I could have proven in intermediate algebra class, definitely college algebra. And would they have understood? Maybe. You're a lot more sophisticated. Any questions on this proof? Okay, so that's a proof that it's 1 to 1. That the composition is 1 to 1 if both s and t are 1 to 1. Okay. By the way, can you go backwards? If s of t is 1 to 1, does that mean that s and t are both 1 to 1?
Yes.
All right, how would you go backwards? Okay, so it's a little harder to go backwards if you think about it. It's not so obvious whether it's true or not. I think I'm going to hold off on it because it's a little bit technical. So this is a forwards proof. There's not an if and only if. Any questions on that? Okay, and there are some reasons, and it has to do with range. So I think I'm going to hold off on it for a little while at least. Okay, now comes a major definition. Okay, like I said, we've already had the most important definitions in this class. What were the most important definitions? All in the same section?
Span, linear
Space,
independence.
yeah.
Subspace.
And linear independent spaces. Okay, those are the biggies. This one is kind of ranked kind of next in the next group. So this is an important one, but it's not span, it's not linear dependence. So those are the biggies. And then is isomorphism. So here's the definition. Very simple. T is called an isomorphism. Let me make it red because it's important enough. If T is both 1 to 1 and onto.
Just thinking about it, would T have to be a square matrix?
Okay. So that's a very complicated question. So the answer is yes today, no in 2 weeks. Don't you hate those answers?
Yeah.
Okay, and I've mentioned this a few times already. So far for all of you guys, when you think of a linear transformation, you're going from Rn to Rn, right? But I've mentioned it pretty much every day that's later on, we're going to say, well, you don't have to go from RM to RN to RM. You could go to, weird stuff, it turns out. And so, yes, it's true for what our definitions are now, but no for the final exam. So that's why it's a big warning. Does that make sense?
Yeah.
And the idea is for the final exam, when we get into the more, a little more abstract stuff later on, T isn't going to have a matrix. And if T does have a matrix, sometimes it'll be a matrix you've never seen a matrix like it before, an infinity by infinity matrix. You ever seen one of them?
Not that I'm aware of, anyway.
Yeah, they can happen, but they're a little weird, trust me. We're not going to get into too much in this class as matrices. But honestly, my dissertation got into it in a deep way. I'm not going there, though. But later, we're going to get into infinity by infinity without saying those words. And then the answer is no. So as long as it's our definition that we have today, instead of in a couple of weeks, the answer is yeah. Okay, so this is a big definition. T is an isomorphism if T is 1 to 1 and on to. And as you mentioned, if we're talking about the definition we've got today, then if you look at the matrix with respect to T, if it's not a square matrix, you're going to have all kinds of problems. Why can't it be true if it's not square?
Look at that last example we did. When it was not onto norm 1 to 1, it was not a square matrix. It was a 3 by 2.
Right, and the problem is that the rank of A, if it's not a square matrix, can never be as big as both M and N. Do you remember that?
Yeah.
Because you can never be bigger than the number of rows, and you can never be bigger than the number of columns. So if the number of rows is bigger than the number of columns, then you can't be an isomorphism. And if the number of columns is bigger than the number of rows, you can't be an isomorphism for those reasons. So you're right on that, as long as we can do it with matrices. And we're getting there in a minute or two. All right, so that's isomorphism. And the nice thing is if you can write as a matrix, it's going to be very easy to prove when something's an isomorphism or isn't. And I'm going to give you 4 letters, which you should be able to tell me for proving it's an isomorphism.
TFAE.
Yep. That's a big piece, and we're going to get there in a bit. At the end of it, that's got our last main thing to do is TFAE, and that's in there. Okay, so now some theorems. So if T is an isomorphism, then T inverse, and in fact, let me write this down, exists and is also an isomorphism. So that's an important theorem. So if T is an isomorphism, then T inverse exists and is also an isomorphism. Why must that be true?
There's a similar reasoning to like how we did it with functions, right? When a function was 1 to 1, then it was, the inverse of that function was always 1 to 1.
Okay, and that was true, and it's going to be true here too. Okay, so right, similar to what we did with functions, you got to do onto also though. And that, but we have to show it exists too. And the idea here is we can move to matrices. So again, at least today, we always have matrices we can look at. So the proof is consider the matrix A that represents T. Okay, So we know about the rank of A. So if T is an isomorphism, then what do we know about the rank of A? It's equal to what?
N.
It's equal to N. And the rank of A is also equal to
M.
M. M. Remember, 1-to-1 gives you, I always have to think about whether it's M or N, but it gives you one of them and on-to gives you the other one. Does that clear? Right, so on-to gives you M and 1-to-1 gives you N. Always takes me a moment to get there. Okay, so in particular, so first thing is therefore M equals N. Hopefully you can all deduce that, right? But then if you know M equals N and you know the rank of A equals N, then T inverse exists. Because, or sorry, A inverse exists, I should write. Is that clear?
Was that a theorem we had?
Oh yeah. What do we call that theorem?
TFAE?
That was one of our TFAEs. Yeah. Yeah. Again, remember that's the most important theorem in this whole class. Okay, and I'm going to be coming down just when you least expect it. We're going to come back to that theorem like all the time. So we know that A inverse exists because the rank is equal to N. Okay, and it's a square matrix, so that means we got a shot. Okay, but now we need to show, so we know that A inverse exists. That's important. So in particular, how do we know that? So now we need to say that Y is A inverse T inverse. That's kind of obvious. Why is that obvious?
Because we said A represents the matrix of T.
Yeah, but, and in particular, A inverse does what A does backwards. That's what A inverse does, right? Okay, that's what we've done that a bunch of times. So if we have a system of equations, you want to solve it, and you look at the inverse, that kind of unsolves it in a way. Okay, so A inverse is the matrix for T inverse. Any questions on that? And that's what we needed. Okay, so we know it's a matrix for T inverse, and we also know it must be, why must T inverse be an isomorphism now?
Because it's A inverse it's A just backwards. But backwards doesn't necessarily change whether or not it would be an isomorphism.
That's what we're trying to prove, though. Can't use it to prove it.
Well, the rank is going to be N.
Yeah, that's what we're going to do. So we know that by TFAE again, it's all part of TFAE. The rank of A inverse is equal to n. Any questions on that? Because we know that A inverse is invertible because it's inverse is A. Is that clear?
Yeah.
And by TFE, the rank of A inverse must be n then, because it's invertible. But now the rank of A inverse is n, which is also m. Maybe I'll even write that down. So now we know that T is invertible. T is an isomorphism. Because you need to show that the ranks work. T inverse is an isomorphism. Any questions on that? It's abstract, so it makes this a little hard. You know, be careful about proof by example. That doesn't work. My job is to do a whole lot of proofs. Your job is to do a few proofs. Just let you know that. Okay. And again, I could do an example, but what's an example going to look like?
Messy.
It's going to look like a matrix, right? T is going to be a matrix, and all you do is make sure it's invertible, right? What's the easiest way to show a matrix is invertible, usually?
Find the determinant.
Yep, find the
Make
determinant.
sure that doesn't equal 0.
Yep, find the determinant, make sure it doesn't equal 0. And that's it. I mean, do you want me to do an example of a matrix and say, hey, here's the determinant? Or do you get it?
Nah, we're good.
Yeah, because I could type out a matrix and find the determinant, show it's 0 or not 0, and say, hey, therefore, you know, the determinant was 0, so it's not invertible, or therefore the determinant, so it's not an isomorphism, or therefore the determinant is not 0, so it is an isomorphism. But that's all you do. Okay, determinant is not always, but it's usually the easiest way to show that you have an isomorphism. Okay. So if S and T are isomorphisms, then S of T is also an isomorphism. Why must that be true immediately? Any thoughts? Or within a line or two?
I can't think of a reason, a specific
That's-
reason why that must be true. It just sounds right.
Yeah. It's not a good proof, though. It sounds right. It's not a good proof.
Both
right,
are
what-
1 to 1.
Huh?
Both are 1 to 1.
Right. So we know, first thing, we're good for not 1 to 1. Why are we good for that?
That's part of the definition of isomorphism.
Right, but how do you know? No, but it's that we know that if S and T are 1 to 1, then S and T are isomorphisms, then S of T must be 1 to 1. How do we know that?
You have a theorem for that.
Yeah, because I just proved that theorem. Because if S and T are isomorphisms, they're 1 to 1. And if they're 1 to 1, then S of T is also 1 to 1. Is that clear? By above theorem. Are you good with that? All right, Y is on to pretty easy now. All right, if you're not sure, let me write it out. So we need to get let's see, U, V, and W. Okay, so let W be in the range of S. Then since S is onto, right, because it's an isomorphism, there exists, just write down the definition, a V such that S of V equals W. Is that clear? Isn't that what onto means? Any questions on that? Okay, but since T is onto, there exists where am I? Just a minute. I think it went too far. I know what the problem was. That's the problem. So there exists a U such that T of U is equal to V. Have I lost anyone there? Any questions on just writing down the definition of onto? Okay, so what is S of T of U? Who can tell me?
S of V.
That's true, but even better,
Is
even
the-
simpler.
W.
It's just equal to W and we're done. That's it. Because remember, to show something's onto, you have to say if something's in the range, then you can find something in the domain that gets mapped to that range space. Does that make sense? And that's it.
Do S and T have to be the same dimensions if they're matrices?
Yes. So let's call it A and B, because we typically use S and T for the letter for the transformation, and then A and B for the matrices that correspond to those S and T.
Okay.
Does that make sense?
Yeah.
So A and B, yeah, they have to be square matrix. Well, they both have to be square matrices and of the same dimension, because we have last time, if you remember, that when you have S and T, S of T, and you look at the matrices, then the composition is a matrix product. Do you remember that?
Yes. Mm-hmm.
So that matrix product better be, you better have the same dimensions, otherwise you can't even do the product.
Got it.
You see that?
Yeah.
If you have two square matrices, you're not going to be able to multiply them unless they're the same.
Got it. Yep.
Okay. On the other hand, if S and T are not isomorphisms, then S and T do not have to be the same dimensions, but they have to be compatible. So if say one is 3 by 5, the other could be 5 by 7. That's fine.
Okay.
But the others could, but if one's 3 by 5, you can't have a 4 by 9.
Yeah.
Okay.
Otherwise, it wouldn't work.
Yeah, you have to be able to multiply the two
Yeah.
in the right order.
Okay.
Yeah. Good question, though. Really good question. Any questions on this right here? So a lot of theorems, but there's not too much to them. Proofs are usually quick. Okay. Guess what? Another theorem. And that is if we have V1 through Vk are linearly independent vectors, and T is 1 to 1. Okay, then T of V1 dot 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 T of Vk is also 1 to 1. Any questions on the statement first? Okay, and then a note is that if V1 through Vk is a basis, then T of V1 through T of Vk is also a basis. okay, for what it spans. How do I prove this theorem? The hint is it's pretty easy.
Well, if we have t of some vector and multiple of them, that's already a basis. And if it's 1-to-1, they're going to be equal to.
How do you
each
know
other.
t of a vector is a basis? We're trying to show that. We're trying to show that we still have 1-to-1.
Mm.
Again, you can never use what you're trying to prove in your proof. So let's go back to, oh wait, then t, sorry, this the first thing is there's a typo there. Should be linear dependent, not 1-to-1. So we're going to show that t of v1 through t of vk is linear independent. How do you show something? How do you show a set of vectors are linearly independent?
You can
So
build
it's
matrix.
1, v1, ... ck, vk equals 0.
Yeah. So let's start there. I was going to do copy and paste, but it wouldn't let me. So let's do it this way. So let C1 T V1 plus C2, actually go ... plus CK T of VK equals 0. So whenever you're trying to prove something's linear independent, you start there. And what's our goal, by the way? What are we trying to show?
That t of v1,
No,
no?
T doesn't even go in there when the goal has nothing to do with the T.
All C's are 0.
Yeah, we're trying to show that C1 equals 0 all the way up to CK equals 0. Okay, well, we know that T is a linear transformation, right? So since T is a linear transformation, I can rewrite this. And what can I do with this? How can I kind of consolidate?
We can write t of c1 times v1.
Yeah, C1, V1, and then what?
Plus t times c1 of v2, c2 of v2.
Yeah, but I'm going to use ... And then CK,
vk.
VK equals 0.
Mm-hmm.
Any questions on that so far? All right, what haven't I used yet?
1-to-1.
I haven't used 1-to-1. If I have T of something is 0, what do I know about the something?
It must be 0.
Yeah, so now I know that the something must be 0. In other words, I can cancel, I can kind of like divide out by T. It's not quite doing that, but that's the idea. So I can get rid of the T because by being 1-to-1, I don't need the T. And I could say CK, C1, V1 plus ... CK, VK equals 0. All right, now what can I conclude?
It's linearly independent.
Yeah, since the first set, I'll just copy and paste the statement. Since V1 through VK are linear independent, that means that the C's are all 0. So C1 equals 0, ... CK equals 0. Any questions on that? That was my goal. So now what the final conclusion is? What's the final conclusion?
T of v1 ... T of vk is linearly independent.
Exactly, because our goal was to show the C's were all 0, and they were. So therefore, the set must be linear independent, the set of T's. And that's the proof. Any questions on that? Okay, so if you ever need to prove linear independence, you always set up this relationship. C1 times the first plus ... plus CK times the last equals 0. And then you're hoping you can end up with all the C's are 0. And if you get that, then you can say you got linear independence. Any questions on that? Okay, so that's nice. So if T is 1 to 1, then we have that mapping from linear independent sets to linear independent sets. Okay, and similarly, that means bases are mapped to bases. Okay, why is that obvious at that point? Who can tell me?
Because both are linearly independent.
Yeah, they're both linear independent, and there's one more thing you have to notice. It's very easy, but you have to like notice it.
Each linear transformation would set up a new basis.
Well, that's what we're trying to prove. It's really easy. That's a hint. Should I tell you? Because if you look at the set V1 through VK, and you look at the set T of V1 through T of VK, it has the same number of vectors. Is that obvious?
Yes.
And we have a theorem that if we have the right number of vectors and we want to show something's a basis, you only have to show linear independence. Do you remember that theorem? So that means that they must bases map to bases, because that was by theorem. Okay, here comes the next theorem. Today is theorem day, but none of these theorems are hard, but there's just a lot of them. So let's suppose V and W have the same dimension. So V and W are now vector spaces. And let's suppose that T maps V to W. Then TFE. One is T is 1 to 1. The other is T is onto. And the third is T is an isomorphism. Why are those equivalent? The hint is I said it about 20 seconds ago. Who remembers? I don't see you all running into it. Because when you do these proofs like above, if you show it's 1 to 1 and it has the same number of vectors, then it's onto and it's an isomorphism, and vice versa. Does that make sense? So it's kind of already been proven because we have the right number of vectors, and that's all you need. So if you have the right number of vectors, 1 to 1 and onto are the same things. And 1 to 1 and onto is an isomorphism because remember, T isn't matrix. So we're talking about matrices here. Any questions on this big theorem?
Wait,
All right.
okay. Could you hold on it for a second?
Sure. You talking to me?
Yeah.
Okay. What do you want me to hold to? Just not move.
Just yeah, don't move.
Yeah, it's not going to be moved, but I might type a little more if that's okay.
That's fine.
And let's see how you can do. Here's the big theorem. Who remembers number one in TFAE? The TFAE.
A is invertible.
Yep. Number two. And honestly, I don't know them in order. I could list them all, but I don't know them. But just name them out.
Determinant does not equal 0.
Yep, determinant of A is non-zero. Number three. We have a lot of these.
Or REF of A equals 1.
Your idea is right. You're saying it wrong though. REF of A
Equals the
equals
identity matrix.
I. Yeah. We don't use the number one, we use the letter I. And one of the problems is that when I type it, it looks just like a 1, doesn't it? Sorry about that. But
The columns of A are linearly independent.
good. The columns of A are linear independent.
As are the rows.
Okay. Good. Column span Rn. And I guess I'd make that N a superscript. And I could say the same thing with the rows. Okay, the rank of A is equal to N. Who remembers some more?
It also equals M.
Yeah, but remember that just by definition, N and M, you can't even talk about it unless we have square matrices.
Yeah.
Just for square matrices. So there is no M in this language, right? I don't know if I've written this one, but I might have. What's the nullity of A?
Rank of A minus N, or N minus rank of A.
Looking for something much easier. What's the nullity of an invertible matrix?
N minus rank.
Much easier. Here's a hint. You only need one symbol.
The Kronecker delta symbol.
No, much easier. It's a symbol a first grader understands. Maybe kindergartner.
I. No, that doesn't make any sense.
All right.
Just trying to think of easy
Not
symbols.
one.
Positive? No.
It's 0.
Oh,
It's 0, right? Because remember, that's the dimension of the null space. And the dimension of the null space must be 0 for A to be invertible. Is that clear? So I'm not sure if I've written that one down, but we've talked about nullity. So I figured we should probably write that one down. So the null, and remember the rank plus the nullity is equal to M. So if N plus something is N, then that something must be 0. It's another way of looking at it. Okay, well, we can add some more now. And that is T. Oh yeah, always does a space. I don't know how to get rid of the space. T is 1 to 1. T being the linear transformation of A. Can you give me a couple more? Now that I've given you one, you should be able to give me 2 more. All you do is look on the same page.
T is on 2,
Yep, T is on 2.
and T is an isomorphism.
And T is an isomorphism. By the way, do you think we're done for the quarter on TFEs?
I don't think we're
No.
nearly done.
We're not even close. Yeah, I warned you, this goes on and on and on. And every time you have some new vocabulary or new idea, there's more to TFE. Okay, and you can trust me on that. It just keeps going. And it's
Will
so
we be able to like take down like TFAE like on a flashcard or something into the final?
remember you get a note card? You can put what you want on it.
All right.
Yeah. So if you need it, then that's what you can put on. Otherwise, you want to put other stuff on. So it's up to you. I don't tell you what you have to put on. But yeah, there's a lot of things in TFE.
It's just you mentioned that it ends up being like 40 something long.
There's a lot. There's a lot. But again, the idea is you're supposed to get used to it enough that you should get it. You know what I mean? I'm not gonna test you saying write down all the TFE because that would be too long a problem for the final. Just let you know that. The final would be a very long final if you had to do that. But again, we have 3 more. So TFE is like the theorem of this whole class. Have you noticed it? Okay. And and by the way, there were others. I'm not going to write this one down because it came from last quarter. What's last quarter's? TFE. How does it match with last quarter? Anyone know?
The cross product of 2 vectors is the determinant of them.
I'll let you know you can never say cross product with TFE. How come?
I'm not sure.
Okay. So when we're talking about a matrix A, it could be a 4x4 or a 2x2. So cross products only work in 3 dimensions. Does that make sense?
Yeah.
So you can't even go to cross products because cross products don't work for anything but 3 dimensions. No, this is last quarter. So should I tell you? Okay, it means that you can, it means that if it is the Jacobian of a transformation, then that transformation can be used in taking a triple integral or double integral. And you talked about that in Bruce's class, right? You just didn't have all this language and stuff. But really, that's what you were doing. Because you had to have a non-zero determinant. Do you remember that? So again, it even worse from last quarter. That's how important TFA is. What I thought I would do, just for, since we have some extra time, since you guys didn't have questions, is let me reshare my desktop. And actually, let's do a few things. Let's go to that one and that one. There's 2 sections. And we're in 5, 3, and 5. Let's see, sorry, 5, 5, and 5, 6. So I'll let you pick a number, either 5 or 6. And then after that, I'll let you pick a number that isn't, if you picked 5, 2, 3, 6, 7, or 8, isn't 1, 3, 5, 8, 10, or 12. So any thoughts? If you want me to pop my screen down, let me write these down so because it's too hard to go back and forth. So 2, 3, 6, 7, 8. And 1, 3, 5, 8, 10, 12. And this is 5, 3, and 4. Let's see, I think they're not too long, so I think I can get to it. So any, so this is 5, 4, for example. Any requests? And this way I'll do a problem like your homework. First one to request, we'll do it.
6.
6 on 5.4?
Yeah.
Okay. Okay, because this will help you out and kind of figure out what you're supposed to do on, say, problem 5, which has the same instructions. Do you notice that? Okay, so find the matrix for the linear transformation that rotates every vector R2 through an angle of 2 pi over 3 and then reflects across the x-axis. Is this, am I in the right section? Let me
No.
double check. And it doesn't feel right. Just a minute. Let's look one more time. Oh, no. It should be 5, 5, and 5, 6. But I can still do number 6 on 5.6. How's that? Just getting to it takes some time. There we go. And you want number 6. Okay, so here's number 6. We're going to define T R4 to R3 as following. T of x equals this matrix times x. Sound good? And then it says find a basis for the image of T and also find a basis for the kernel of T. Okay. So to do that, what's our first step?
I think we should try and find T.
Well, we have T.
Oh, I see.
You definitely don't want to get more complicated than its matrix. Here's a hint. 4 letters.
RREF.
Good. RREF. Definitely not TFE. Okay, so I'm gonna go symbol lab. Sound good? And this was a 3 by 4. And 3218. 22 negative 26. And then 11 negative 13. Any questions on popping into symbol lab? And I hit go. Okay. And there it is. So let me write it down because I'm going to be leaving the screen. So we have 1, 0, 3, 2, 0, 1, negative 4, 1, 0, 0, 0. Actually, instead of doing that, let me do the following. It'll be faster. All right, let me go new share. Okay, so here's our RAF matrix. So again, from the question, we wanted to find the image in the kernel. So how do we find the image in the kernel? And I guess I should show you the original matrix too, because it'll be confusing if we don't have that. So let me get that. This was number 6. That's not what I want. Just a minute. All right, so what is the image of T? So how do we get the image of T? First thing, what dimension is it? Is it an R2, R3, or something else, R4, R10?
Is it going to be an R3?
Okay. Yeah, it's going to be an R3. And what is it?
Is a column space?
It's the column space. So in particular, again, we've done all the work. So what is it? Now, what vectors is it?
It's
You should be able to read.
3, 2, 1, 2, 2, 1.
Good, good. So it's going to be 3, 2, 1. Oops. Because you can always take columns from the original matrix that are pivot columns, and that will give you the image and the kernel. So how do we get the kernel? And the hint, now we look at the REF and don't have to look at the T itself anymore.
The row space of the pivots.
We can
That
write
won't quite work, actually. That would be the row space. And the row space is not the kernel, it turns out.
x1 plus 3x3 equals 2.
Right. Okay, so we can write that way if you want, because that might help you see it. So we can rewrite it as, do you mind if I call it W, X, Y, and Z? Easier to type?
Yeah.
So W plus 3Y plus 2Z equals 0. It always tries to capitalize that W. There we go. And the second row tells you what? What equation do you have?
X plus negative 4y.
I'm going to write X minus 4y.
Plus z equals 0.
Okay. So now, if you remember, if we want to find the kernel, what we do is we need to find a basis. And what are our free variables, by the way?
C is a free variable.
There's 2 free variables. That's a hint.
U, z and w.
No, W is not a free variable.
Y and Z.
Y and Z. Y and Z. Because remember, the first 2 columns are pivot columns. The ones over here. So that's the X and the Y. That's the, W and the X. And then the Y and the Z are not pivots. So that means Y and Z are the pivots, are the free variables. So that means I'm going to let Y be 1, Z be 0. And if that's true, then W is negative 3. And X, if Y is 1 and Z is 0, X will be 4, Y is 1, and Z is 0. And then I let Y be 0 and Z be 1. And if I do that, W is negative 2. X is going to be negative 1. And then Y is 0, Z is 1. And we've now found a basis for the kernel of our transformation. Any questions on this? Okay, it is 2:45, so I'm going to stop the share and stop the recording.